Hey, so guys, Elizabeth has already put this on her list of things that she needs to work on. Which is interesting because we haven't really done any. You just know this is going to be weird, right? Yeah. So guys, let me explain to you the way that we're going to handle chapter 20. And so chapter 20, as you start to look at it, it feels like really deep waters. And as you look at it in the Princeton Review book, all the more so, especially because you haven't learned any of it. And so really that wasn't Princeton Review, that was Princeton Learn It for the first time. So guys, what I would encourage you is let me take a swing at this. And then if you go back maybe and look at that Princeton Review stuff, you might go, okay. But guys, with that said, we're going to sort of handle electrochemistry in an appropriate fashion. Guys, we could spend weeks digging to the bottom of everything that is in chapter 20 and in the Princeton Review book. But guys, from my experience, this all distills to 2 days worth of material. Oxidation reduction chemistry, which is what we're going to do today, and then guys, voltaic cells, batteries, and that's what we're going to do when we get back. So today, guys, we're going to talk about the fundamentals of redox chemistry, oxidation reduction. We're going to talk about the fundamentals of redox chemistry and how to balance redox reactions. When we're done with that, I'm going to then help you understand what this portion of this is going to look like on the AP test. And guys, I'm going to tell you right now, we are going to dig deeper into this today than you will see on the AP test. The reason that I do that is because I know what's coming in college, and you need to be able to do what I'm going to teach you today. But then guys, on the AP test, it's even simpler. And so you'll see that this goes better. And then guys, when we come back after spring break, we're going to talk about in-build batteries, and then we're all good to go. So I think you'll feel better about this in the next couple days. So boys, are you guys okay? Okay, and then we're going to, and you guys I know that this is important and you can always watch the screencast. The only problem is you're distracting me. So if you need another couple seconds, that's cool. If you need more time, just go next door. Yeah, that's totally fine. Okay, so guys, let me tee up the ball for you here relative to this redox stuff. So guys, back in chapter 5, when we did aqueous chemistry, we did a really quick touch on oxidation reduction. Today we're going to go deeper. And so guys, let me sort of give you an analogy for the way you need to interact with this material. So, and I don't know, have any of you received your mission calls yet? Sorry, hard left turn. It'll make sense in a minute. None of you have received your mission calls yet? Oh, interesting. All right. But guys, at the end of the day, you all know people that are missionaries, right? And if you talk with missionaries that are serving in a location where it's a non-English speaking mission, and if you talk with these missionaries about how did you know when you really knew Italian, Portuguese, Spanish, French, whatever it was, how did you know when you really knew the language? And their answer will be, you dreamt in that language. Because guys, when you start to acquire a language, you don't know it, but you're translating. And actually, you probably know it. You're thinking, if you're in a Spanish-speaking mission, you're thinking it in English, translating it to Spanish, and then the words come out of your mouth. You know that you've finally learned the language when it becomes your thinking language. And therefore your dreaming language. And guys, that is your goal with oxidation reduction. Simply those two terms. Guys, if you look at the first page of notes there, that's not the title slide. If you look at the first page of notes, guys, there's all the definitions about oxidation reduction. But guys, you need to get this deep enough in your head that you're not thinking, okay, oxidation is the losing of electrons and the charge of the thing goes up. You just got to be able to look at that and go, that's oxidation. That's the place you want to get. So, guys, the question then becomes, how do you get there? And the answer is repetition. So guys, when you're working on this homework, when you're looking at Princeton Review, when you're doing this, guys, please don't let oxidation and reduction be words that you read over, like all of the names in Shakespeare literature, because you can't pronounce them, so you just read right over. Actually, the Old Testament too. I do that all the time. I'm like, I can't pronounce Meshivafeth, and so I just go, oh, that guy, and I just keep reading. Right? Guys, please don't let that be the case here. Let it be oxidation. Okay, what does that mean? Reduction, what does that mean? So guys, with that said, what does it mean? Well, guys, let's talk about it. So guys, when we talk about oxidation reduction, we're talking about a transfer of electrons. Please, in your brain, do not try to map this onto acid-base reactions. I have people that go, okay, acid-base is a transfer of protons, so it's just like that, only with electrons. And guys, please do not go there. Those connections will fall apart as you get into college. So it is a transfer of something, but please don't try to map it onto your understandings of acids and bases. So with that said, guys, the way that we know oxidation reduction happened is because the charges of the reactants and the products change. Guys, just like black holes, we can't see black holes, but we know that they exist because we see how things around the black hole changes. Same thing here. Guys, we can't see electrons move, but we find evidence that electrons are moving because when electrons move, charge changes. So then it goes like this. And guys, this may be something that you want to start to tear apart. But guys, fundamentally, maybe you start underlining things to try to become more conversant in the language. But guys, the bottom line is this. Electrons are transferred from the atom that is oxidized to the atom that's reduced. So guys, at this point, and I know you don't have a lot of room in your notes, but maybe you find a place to scratch this down. Guys, I find it helpful if we talk about where the terms oxidized and reduced come from. Because if you understand the origins, you'll probably better understand the concept. So guys, let's talk oxidized first. When you hear oxidized, what element do you think of?
Oxygen.
Hey! So guys, let's talk, shall we, about oxygen. So guys, looking at oxygen, how many valence electrons? 6. So how many electrons does it want?
2.
And that's quite a few. It's more than 1 or none. But guys, in addition to that, well, let's do a little AP review. Guys, oxygen doesn't have a lot of shielding. Oxygen has a strong effective nuclear force. Remember that from PES? Guys, the idea is oxygen's got 8 protons. It only has 1 inner shell, core electrons, the s orbital. And then, guys, outside of that, it's got 6 electrons in its valence shell. And, guys, there's not a lot of shielding. So those 8 protons are very, very effective, if you will, at influencing its valence shell. We call that electronegativity. And so, guys, the idea is this. Oxygen can take in 2 electrons. Oxygen is wildly abundant in our atmosphere and other places. And, guys, in addition to that, it's got space for quite a few, and it's electronegative. So, guys, why do we call losing the transfer of electrons, that is, so it said electrons are transferred from the one that's oxidized. So, guys, why would we call that oxidation? With all of that background, why do we call that oxidation? It's what oxygen does to things. Guys, we have a term for that. It's called rusting. Exactly. So guys, when they were studying fundamental reactions in like the late 17 and early 1800s, they started to realize that oxygen, especially towards metals, was able to rip electrons off of these metals. So they said if oxygen is doing this to metals, again rusting, they said let's call that oxidation because we know that oxidation is doing that to things. Does that logic make sense? So guys, oxidation is losing of electrons. So guys, why on earth would we call gaining electrons reduction? The charge is being reduced. So the thing that is gaining electrons, guys, that thing, as it picks up electrons, its charge goes down, and we call that being reduced or reduction. Does that make sense? Okay, so now guys, let me throw all the corny bits at you. And the corny bits go like this. So how do we think about this? And we now know that oxidation is the losing of electrons and reduction is the gaining of electrons. And guys, eventually that's got to be a part of your thinking language. But guys, the rules of thumb are this. This is the one that I like. The charge of the atom that is reduced. Get it? Kind of snazzy. But guys, oh wait, is it not on there? Shoot, write it down. This is BYU's trick. BYU likes to go with oil rig. Huh? You learned it earlier in the year. I shared it with you then. Oxidation is loss, reduction is oil rig.
It's way better than the one in the Princeton book.
What's in the Princeton book?
Something about a lion. Yeah, the lion. I'm like, no.
Lion? What is it?
I don't have the loss is oxidation.
Good. It sounds meaningful. At any rate, guys, the idea is this, and this is an idea that you need to understand. You'll see this in multiple choice. So guys, you need to understand this idea of agency. And Michael got to this a moment ago when we asked the question, why do we call losing electrons oxidation? And Michael's observation is, because that's what oxygen does to other things. Guys, there's two ways to think about this. When we think about oxidation, oh shoot, there we go. Okay. When we think about oxidation and reduction, we're talking about what is happening to the thing. So guys, if something is oxidized, it's losing electrons. If something is reduced, it's gaining electrons. But guys, we can also talk about, oh, I zoomed it off the screen. Guys, we can also talk about agency. And when we talk about oxidizing agents and reducing agents, we are now talking about what that thing does to other stuff. So guys, if this doesn't make sense, try this. We've got iron and we've got oxygen, and I'm not going to draw this diatomically just for clarity. And so guys, what is oxygen going to do to iron? It's going to take electrons. Let's say one, it's really more than that. But guys, oxygen is going to take electrons from iron. So guys, see if you can do this in your head. Ready? See if you, maybe not, we'll go slow. This is new to you. Guys, what happened to iron? It was oxidized. It lost electrons. Who did the oxidizing? Oxygen. So that makes this the oxidizing agent. So when we talk about agency, we're talking about what it does to the other guy. So guys, iron was oxidized. Oxygen is the oxidizing agent that caused the oxidation. Does that make sense? I know. But now, if you look at the oxygen, what is happening to the oxygen? It's being reduced. It's gaining electrons. It's being reduced. So guys, that's what this is all about. So the oxidizing agent is the thing that removes electrons. It causes oxidation, but in fact, if you're focusing on that substance, it is reduced. So guys, when we talk about oxidation and reduction, we're talking about what happens to the thing. When we talk about agency, we're talking about what it does to the other guy, and in fact, what happens to it is the opposite. So oxidizing agents are reduced because they're taking electrons, causing oxidation in the other guy, and then reducing agents are causing reduction in the other guy. So they're giving away electrons, so those are oxidized. So holy buckets, y'all. I know that this is like your first day in the MTC trying to learn a language, because this will come. The language will come. But what questions do you have about the concepts? You okay? You're good? Good? Okay. So guys, with that said, let's do this. So, why can I not? Oh, there we go. So, yep.
Does the other thing have oxygen in it, or is the oxygen outside?
Help me with other thing.
I'm saying there's the oxidation agent. Isn't that going to be like the other molecule? Part of the other molecule?
Could be, or I mean, so if we want to put this in a more, if we want to put this in a more realistic context, it would look like this. Iron, in the presence of oxygen, forms iron 3, so this would be 2. So it forms iron 3 oxide, which is the most common form of rust. This needs an E. So does this get you? So the idea then is if we were to track electrons, and we're going to learn how to do this in a minute, the iron is, well, we need to balance it. So that would be 2. So 2 and 2, and we need to double this, and that gives us a 3, and then this becomes a 4. But so when it's balanced, we would find out then that the iron is actually losing 3 electrons, but there's 4 of them, so that's 12. And then anyway, so I'm not exactly sure what your question was, but this is what it is. That did we get where you needed to go?
As we go ahead.
Try this. I think we're about to go where your head is going. Okay. So guys, consider this. Consider the reaction between hydrochloric acid and zinc. You may remember this from Gen Chem last year. Remember, this was the giggle reaction when you put the zinc in the hydrochloric acid. John loved this one last year. Very meaningful to him. And you put the zinc in the hydrochloric acid and it bubbled, and we collect the hydrogen gas, and then we made it explode. And went boop. And you did it like 11 times because you thought that was really funny. But guys, at the end of the day, what we need to be able to do is recognize that this is actually an oxidation reduction reaction. So guys, what I'm going to encourage you to do, well, do we need to draw beakers? Or... Kale, you're killing my joy. You know how much beakers mean to me. What about this? Guys, when you picture this, are you picturing in your head a solid chunk of zinc? And when you picture hydrochloric acid, are you picturing hydrochloric acid squirt bottle? And guys, when you picture this, are you picturing bubbles? And when you picture zinc chloride, Kale, I got to do it. When you're picturing zinc chloride, please be picturing this in water. Yes? Okay. So guys, what we need to do then is this, and it's in your, I believe there's spaces in your notes. How did I space this out for you? So, guys, we need to answer the questions, and we're not going to follow this exactly. But we need to, first of all, realize that this is an oxidation reduction reaction. And in order to do this, and guys, we learned this back in September, but we're not going to treat it like review. Guys, we need to assign oxidation numbers to these elements. Do this with me. Guys, oxidation numbers happen at the elemental level. So guys, let's just see if you remember. Do you remember the oxidation number for elements in their elemental states? Hey, write it down. Guys, you know what? I want to make these a different color. So guys, the elements in their elemental states are 0. This is the elemental state of hydrogen, even though it's H2. So now, guys, we need to know the elemental states of the hydrogen and the chlorine in HCl. So we know that we've got hydrogen, which is +1. So if hydrogen is +1, what does the chlorine have to be? -1. Then, guys, we can go over to zinc, and we know how to find these charges. This is -1, so what's the zinc? +2. So now, guys, you've got some... Oh, go ahead.
So oxidation plus minus goes to 4.
So technically... And they will not... So, guys, Jared's question was, is it plus the number or the number plus, right? And so on the AP test, they won't care. With that said, let me tell you the answer up here. So this should technically be +1, and this should be -1, because those are oxidation numbers, because this is covalently bonded. Technically, this should be 2+ and this should be 1- because it is a salt. And as a result, these are not oxidation numbers, they're technically charges. We use them at some level interchangeably, and they won't hold your hand to the fire on the AP test, but understand as you get deeper into this, there is a difference. Okay, so now guys, this. We're going to take this from two different directions. So, guys, who was part of the oxidation reduction chemistry? And in order to know, we need to know whose charges changed. So, guys, did zinc's charge change? So it was part of the chemistry. What I like to do then, and I would encourage you to do this, is do that. You're looking for pairs. Then, guys, what about hydrogen? Did its charge change? Yeah. There's another pair. Then what about chloride? Did its charge change? It did not. Ready for an interesting tie back? What does that make chloride? Spectator. Guys, you would have known this was a spectator had you drawn beakers, but Kale forbid us to do it, and so now you have to just realize that its charge didn't change and therefore it's a spectator. We are all better served by beakers. Yeah.
So,
Yeah. Yeah. They are. You will never find, and so quick review. Guys, remember the diatomics are iodine, bromine, chlorine, fluorine, oxygen, nitrogen, and hydrogen. Those elements are all so reactive that you'll never see them by themselves. If they have nobody else to react with, they'll bundle together in groups of 2. That is their elemental form, and as a result, their oxidation numbers are 0. Yeah. Does that have something to do with lions?
I see it.
That makes that so much easier, except for it doesn't.
I mean, I don't know, they just kind of like look like it. You can kind of just tell.
It's a stinking L flipped upside down. Put your finger on iodine, go up till you can't, go left till you run out of red, and then go to hydrogen. Have, no, oh, so no is actually the N and the O.
Or the of could be. No, of ice cold.
Have no fear of ice cold beer.
Yeah.
Okay, so back to this. I'm guessing that is not a BYU acronym, given that it actually breaks the honor code. All right. Good night. Why do I feel like I just got dumber? Okay, so guys, the bottom line is this then. We need to not only be able to identify who's changing, we need to be able to now identify how they're changing and by how much. Shall we? So guys, zinc starts at 0 and goes up to -2. Quick, oxidized or reduced? Oxidized or reduced? Oxidized. How do we know it lost electrons? How do we know its charge became more positive? Guys, that's what this has got to feel like. Zinc 2+, oxidized. Okay? So guys, this is the dude that is being oxidized. Now, by how much? How many electrons? 2. 2 electrons. Now we got to find the dude that's being reduced. And obviously, it's the other one. And we notice that the charge goes from +1 to 0. Wait a minute, +1 to 0 is only 1 electron. But there's 2 of them for a total of 2 electrons. Guys, this is the law of conservation of electrons. This is what makes balancing redox reactions one of the most ridiculous things you'll ever do in your life. And we're going to do 2 of them in about 5 minutes. It's horrible. So now, guys, this. I need you, I know you probably won't write them down, so don't. But, guys, in your brain, I need you to be able, actually, I lied. I want you to write it down on the paper. And it's even in the thing. Which substance is oxidized? Write it down. Which substance is reduced? Write it down. I want you to write it down. Which substance is oxidized? Which substance is reduced? You guys all committed to an answer? You good? Okay. I would be willing to bet you that all of you got it wrong. Here we go. Now you're scared. Which atom is oxidized? Zinc. Y'all put zinc? Which thing is reduced? Not hydrogen, not HCl. Cl is a spectator. What is reduced? Hydrogen ion. Guys, it matters. Hydrogen, and guys, do this please in your head. Hydrogen and hydrogen ion couldn't be more different. Hydrogen is a diatomic gas that bursts into flames. Hydrogen ion is a proton. It's the foundation of acids. Guys, hydrogen ion and hydrogen couldn't be more different. The thing that's being reduced is hydrogen ion. Does that make sense? Okay, now guys, this, and we're going to do this here and then we're going to talk about it more in a minute. But guys, now what we need to acknowledge is we've got an oxidation going on here and a reduction going on here. And guys, we can now separate these and write them as 2 separate processes. Guys, join me in doing this. So here's what we've got. Find a place to write this on your paper. Guys, we've got zinc. And in this reaction, what is happening to the zinc? What's happening to the zinc? It is being oxidized. It's losing electrons. But guys, stop. When we write losing electrons, we do not write it like this. Instead of writing losing electrons like this, we write it like this. We get zinc and 2 electrons. That you want to write down. So guys, when we separate these apart, the thing that is being oxidized is not zinc minus electrons. It's ion plus electrons. And you guys understand technically they're the same, right? Because if you subtracted electrons from both sides, you'd get zinc minus 2 electrons is zinc 2 plus. But we always write it in the positive sense because we're positive people. You okay? So guys, what is the other thing that happened? Well, we've got 2 hydrogen ions. What did those 2 hydrogen ions do? They gained how many electrons? 1 each for a total of 2. And that formed diatomic hydrogen molecule. You okay? So guys, 2 important observations. This number is the same as this number. That is the law of conservation of electrons. If those numbers are not the same, you didn't balance the equation properly. But then guys, in addition to this, we will always write these equations in a positive light, if you will. But then guys, you ready? Which one's reduction, top or bottom? Which one's reduction? What does reduction mean? Gaining electrons. Where are we gaining electrons? Down here. This one's reduction, this one's oxidation. One will always be oxidation, one will always be reduction. You've got to have somebody losing electrons and you got to have somebody gaining electrons. Yeah? Not in this class. Yeah, no, not often in this class. They maybe in multiple choice they would huck a complex redox. And guys, we didn't say this. Oxidation reduction is distilled to the term redox. So if you hear redox, think oxidation reduction. They might throw. Actually, you know what? We're going to look at an example of one. You'll see. Yeah, so you can have multiple things being oxidized and reduced. We're even going to look at, so not frequently, but yes. The reason that didn't come to my mind is the stuff that we're about to do is stuff that you won't see on the test. Incomplete. It'll make more sense in 10 minutes. Okay, so guys, you good on these ideas? You ready for this? Follow along. Look at what we did. We took a reaction and we broke it into 2 halves. One of those is an oxidation reaction. One of those is a reduction reaction. And guys, if you turn to slide 1, 2, 3, 4, 5, 6, see where it says half reactions? I'll go there in my notes. Guys, these things that we wrote at the bottom of the page are what we call, and my screen's going to freak out. Guys, these things at the bottom of the page are what we call half reactions. So guys, half reactions are the redox processes that we can separate into one that represents oxidation, one that represents reduction. But guys, as we look at this, please notice the trend. I'm going to say it rather than ask it. So guys, this is our oxidation. Think about this. Make this make sense. In oxidation, the electrons are a product. Does that make sense? In oxidation, the electrons are a product. In reduction, the electrons are a reactant. And guys, that's why we write them in a positive sense. We don't say zinc minus 2 electrons, because then they would both be on the reactant side. We say zinc yields zinc ion plus electrons, and then we've got electrons being a reactant and a product. And oxidation, it's always the product. Is that okay? Okay. So guys, we just skipped over we covered a bunch of stuff differently. So now what we get to do is this. Guys, you are now going to learn how to balance redox reactions. This is horrible. So guys, I've been doing this for a long time, right? I'm on a streak. I have done this in front of students for the last 2 years without making a mistake. Up until 2 years ago, I am about 70% bad. Guys, seriously, I even know what the answers are. And these things are so bloody, stinking complicated. And I promise, sometimes I make mistakes because my head is soft. Sometimes I make mistakes because I do it to drive home a point. Because I promise you, I'm not trying to make mistakes. But here's the thing that I ask. You know how in chess, I think this is really a rule, that the move doesn't count until you take your hand off of it? Is that really a rule? Oh, when you hit the timer. Okay, so guys, this is my agreement. What I wrote doesn't count until I take the pen off the screen. Okay? With that said, guys, these are the steps. These are the steps to balancing oxidation reduction reactions. Step number 1, write the half reactions. Then balance each one of the half reactions, and the way to do this is you balance other elements first, then you balance the oxygens by adding water, then you balance the hydrogens by adding protons. Then at this point you balance the charges of the half reactions by adding electrons to the side with the greater all positive charge, thereby reducing the positive charge to become more negative until it balances the other side of the half reaction. Once you've done that, then you multiply one of the half reactions by some multiplier that then makes the number of electrons in both half reactions the same. At this point, you bring the two half reactions together and you simplify. Once you've got to that point, if you're in an acidic environment, you're done. If you're in a basic environment, because there cannot be free protons in a basic environment, you add as many hydroxides to both sides as you have protons, converting those free protons into water, and then that sort of respects the fact that it's in a base. Got it?
What? Yeah, you still missing 2 steps.
I know. But check your work, curl into a ball, and cry like a child. You're right, actually, but what I find is that as I crumble into a ball, I start crying on the way down. So it really happens. Yeah, it's a bimolecular step. You actually, yeah. See how I just did chemistry there? You guys ready? Uh-huh.
Isn't it always instead of H?
So many questions. If only you had a teacher to teach you how to do this rather than you learning it from a book. You realize we call that high school and the other is called college. Unless you're at NYU, at which point you go after your professor and they fire them. That was so snarky. Here we go. Oh, wait. All right, guys. Oh, look at that little cutie. Oh. Iodide ion and iodate ion reacting to form the I3. Oh, so cute. Let's balance it, shall we? All right, guys, I need to grab a fine point pen. Typically at this point, I recommend a moment of silence. And I'm going to get a white screen. So guys, it goes like this. If I screw up recopying the equation, that doesn't count. Because that's just dumb. That's not work. Okay, so here we go. And by the way, guys, do you have a blank? Is there a blank sheet? You may want to just flip over to the very tippy back of this packet and split that page in half. These are... I know, but I'm afraid it's not going to... Well, you'll make it fit. You can just do it on the slide, and I think you'll be okay. Okay, so I minus plus I03 minus yields I3 minus. So guys, as you look at this, the first thing that you should be thinking to yourself is, where'd the oxygen go? Right? And then the other thing you should be thinking to yourself is, how can we have two reactants in one product if this isn't synthesis? The answer is, guys, you're about to boldly go where you have never gone before. So this would be my advice to you. Ignore it at your own peril. Split your working space with a vertical line that goes down about half the way. You can always make it longer. Now, guys, we need to write half reactions. But we only have one product. Jared, this is to your thought. One of the half reactions is I becoming I3 minus. You know, guys, I'm going to write that a little lower just because I'm afraid this doesn't count as a mistake. You have, oh wait, hold on. Ha! I have lines. I've never thought to do this. So we have I. Is that going to be hard to see because the lines...
It's fine.
Don't ask. I'm going to try maybe a thicker pen. Okay, so guys, it goes like this. We have I minus, hey, old dog, new tricks. Here we go. Then our other half reaction, I already screwed up.
Keep your finger on the board.
It's fine. We're distracted with the lines.
I got all excited about the lines. Shoot, no, no, it's a loss. I'm done. For the rest of the day, I'm a loser.
We should just go home and get the day over as fast as we can.
Just put it behind us.
Really hard.
Like that. I know. This means I can't. So really what this means is I can't retire on a year where this goes bad. Man.
But what if you just get too old that you just can't do it right?
I kind of feel like that right now, frankly.
And you just can't retire.
Oh. You know, the thing that's really sad about that is not a majority, but close to the number of, especially the people that I've been especially close with here at Orem High School. Within a couple years of their retirement, they've either become severely sick or died. Yeah, it's really weird. Like cancer, lung disease, strokes. Yeah, it's really weird. Like the underlying implication is Orem High School is keeping us alive. And that's not good. All right, guys, you ready? What? Okay. No, I got to take a deep breath. Because this isn't the hard part. And Not my fault.
Not your fault.
Okay. All right, we got to stay focused here. So guys, now we need to start balancing these equations. And the first thing that we do, and guys, for some of you, this is going to feel like additional work. Trust me on this. Guys, you want to do these in lockstep. Don't let one get ahead of the other. Let me show you what I mean. So guys, we're going to play with this one first. Did I do this right? I negative, I3 minus, IO3 minus, and I3 minus. Okay, is that right? Okay, I'm now doubting myself. Okay, so now guys, the first thing we need to do is balance elements that are not oxygen or hydrogen. So in order to do that, we need 3 I minuses yields I3 minus. And then guys, on the right, similarly, we need 3 IO3 minuses yields I3 minus. Step number 1 is balance all of the elements that are not oxygen or hydrogen. Now guys, remember this, water before acid, right? When you dilute acids, it's water first, acid second, right? Water before acid. Water before acid. So guys, why do we need water? Because it's where our oxygens come from. But guys, you'll notice we don't have any oxygens over here. Rewrite it. I3 minus yields I3 minus. Guys, just trust me on this. I know it feels like extra work, but if your columns get out of sync, you're going to die. So over here, we have 3 IO3 minuses yields I3 minus plus 9 water molecules. Do you see how we balance the oxygens by adding water? You okay? Yeah, do you see that here we have 3 times 3 is 9 oxygens. So now we have 9 oxygens on the right. You okay? Okay, now guys, we've got to balance the hydrogens by adding protons. Water before acid. Acids is protons. Here we don't have any, but we're still going to rewrite it in an effort to keep these in sync. Now guys, on the right we have 18 protons. This means we need 18 protons over here plus 3 IO3 minuses yields I minus 3 plus 9 Wawas. Now we're grooving. Okay, so now guys, this is where this gets a little tricky, brainy. I'm going to switch colors, and am I now blue? Okay. Guys, now we need to balance charges. My strong suggestion to you is don't try to do this in your brain, write stuff down. So on the left, do you see that we have 3 iodides, each one minus 1. So the total negative charge is -3. I'd strongly encourage you to write that down. Then guys, on the right, what is our total negative charge on the right? -1. So now guys, what we've got to do is we have to add electrons to make those the same. So which side, right or left, are we going to add electrons to make the overall charges the same? On the right. We need to bring -1 down to -3. So how many electrons do we add? 2. So now guys, let me switch colors again. So now we're going to go 3I minus yields I3 minus plus 2 electrons. Do you now see that we have a -3 charge on both sides? You okay? Now, similarly, on the right, guys, what is our total charge? Sorry, right-hand half reaction. But guys, what is our total charge on the reactant side of that? Plus 15. Do you see it? Guys, we've got 18 here, we've got 3 there. So this is plus 15. So guys, what is our total charge on the right side? Minus 1? Is that okay? So how do we make these the same? Which side do we add electrons to? The left. Because we've got to bring 15 down to -1. So how many electrons do we add? 16. So switching back to red, we go 16 electrons plus 18 protons plus 3 IO3 negatives yields I3 minus plus 9 water molecules. We okay? You good? Is everyone settled and done writing? You're good? Which one's oxidation, which one's reduction? Don't think. Which is which? What's the left? Oxidation or reduction? What's the one on the left? This is losing electrons, so this is oxidation. This one is gaining electrons, so it is, what if they're both oxidation or both reduction? You screwed up and you have to start completely over. So guys, they will do this to you. On the AP test, they will give you, well, we'll talk more about it later. Sometimes they will just give you, and I'm going to erase this. Sometimes they'll just give you something like that and they'll say, which is this oxidation or reduction? Now let's keep going. Now guys, the next step is this. We need to honor the law of conservation of electrons. We've got 2 coming out and we've got 16 going in. Those have got to be the same. So we've got to multiply the reaction on the left by 8. So now we have 24. This doesn't count as a mistake. I was going to leave myself more space, but I don't need to. So 24 I negatives yields 8 I3 negatives and 16 electrons. Are you out of here? Okay. Have a good break. So guys, at this point, you don't need to rewrite the one on the right, because you're done. Draw a big old horizontal line. And now, give yourself a lot of room. We bring everything down. This kind of feels like Hess's law. 24 iodides. That's our one reactant on the left. Then we need to grab our reactants out of our other half reaction. 16 electrons, 18 protons, and 3 IO3 negatives yields 8 I3 negatives, 16 electrons, an I3 negative, and 9 waters. Man, after that first mistake, so maybe I made a mistake. So we've got 24 iodides, 16 electrons, 18 protons, 3 IO3s. Then over here we've got 8 I3 negatives, 16 electrons, 1 more I3 negative, and 9 waters. I think I'm okay. All right, now guys, we've got to simplify. 16 electrons go. We don't have iodides on both sides. We don't have protons on both sides. We don't have IO3s on both sides, and we can combine those. So guys, at the end of the day, we've got this. 24 I negatives plus 18 protons plus 3 IO3 negatives yields 9 I3 negatives and 9 molecules of water. That's the balanced equation. Oops, I lost a leg.
So the electrons are always canceled in the balanced equation?
If they don't, if these don't cancel, you did this wrong. Yeah.
If we have to add a hydrogen ion to the reaction in order to make it work, or not work, does that mean that oxidation reaction only have to increase?
That's a good question. So do these necessarily then only happen in acidic environments, or right? So some of them, but you'll notice, I'm a little scared to do this. Let's see what happens. If I go back here, you'll notice that it specifies in an acidic environment. So some of these actually, yes, they only work in the presence of acids. That's why iron rusts so much more readily in acidic environments. Also in salty environments, it's a related deal. Yeah. So guys, holy buckets, right? We're going to do it. Oh, go ahead.
If there was two products, is there two products?
Hey, guess what we're going to do next? Look.
So do you just line up like CU?
Here we go. So, guys, no. So what you're going to do is this. Guys, this is your next slide. Take a look. Copper is going to hook up with copper. Nitrogen is going to hook up with nitrogen. Guys, even if you're looking this and going, this is money, I got it. Guys, do this with me anyway. This one's different. Sticking with our color scheme, guys, we are going to, let me rewrite this equation. So we've got Cu2 plus N2H4 yields Cu metal and N2 gas. So guys, same drill, center of the paper, go about halfway down. That doesn't feel like center of the paper. Okay, so now guys, how do we do this? We keep our elements together. So one of our reactions is copper going to copper metal. Oxidation or reduction? Reduction, +2 to 0. We already know that this is reduction. See guys, that's the level you've got to see this. I didn't even have to think about it. I look at, oh, that's reduction. Because I know that when metal ions go from positive to 0, you'll have more experience with this in lab. Then guys, our other one, ooh, we'll make it work. No, we won't. Okay, then our other one is N2H4 yields N2. Guys, go through the steps. You ready? Step number 1, balance all of the elements except for oxygen and hydrogen. Done. Right? Coppers and nitrogens, we're done. Don't rewrite them if you don't write them both if you haven't done anything to either one. So then guys, water before acid. So now let's balance the oxygens. Done. Now let's balance the hydrogens. Now we've got some work to do. So this doesn't need anything, but we're going to write it down because it's good to keep them in step. Then guys, here we've got to balance the hydrogens. By adding water. Oh, got it wrong. By adding hydrogen, sorry. By adding hydrogens. Okay, so we've done atoms, we've done oxygens, we've done hydrogens. Now we need to balance charges. We've already identified the one on the left as being reduction. So let's prove it to ourselves. Can we just kind of do this in our head? This side is +2, this side is 0, so we add 2 electrons to the left. Is that okay? So 2 electrons plus copper, 2 plus, yields copper metal. Now we can demonstrate that this is reduction because the electrons are on the left. Then guys, on the right, this charge is 0. This charge on the right is +4. So we've got 4 electrons plus N2H2. Oh, look at what I did. I screwed that up too. Wow. I'm really on a roll. This should be N2H4. It's like, that doesn't look right. What? Yeah. Wow. I'm really screwing this up. Sorry, guys. This is just really crazy. Okay, so here we go again. N2H4 yields N2 plus 4 protons plus 4 electrons. Now guys, we need to make our electrons balance. Is it okay to say that we need to multiply the left side reaction by 2? So now we've got 4 electrons, 2 coppers, ion, 2 copper metals. Then guys, at this point, we can now draw our horizontal line and bring these together. So I've got 4 electrons. Actually, I'll move that down a line. We've got 4 electrons, 2 copper ions, an N2H4 yields 2 copper atoms, an N2, 4 protons, and 4 electrons. Did I do that okay? I think so. Then guys, we cancel, and our electrons have to go, as Michael pointed out. If they don't go, we balanced it wrong. And that's the only thing that goes. So guys, we end up with 2 copper ions and an N2H4 and 2 copper atoms and a diatomic nitrogen and 4 protons. Are we good? Guys, we're not done. Here's why. Notice that in our product side we have 4 protons, and that would be fine except for this. We are in a basic environment. And in a basic environment, we do not have extra protons. In a basic environment, we have extra hydroxides. So guys, what we've got to do is we've got to get rid of these free protons. And we do that by adding, and free, not 3, but free. We've got 4 free protons. We've got to add 4 hydroxides to cancel them out, which means we've also got to add 4 hydroxides to this side. Right, so now we bring this together and we go 4 hydroxides plus 2 copper ions plus N2H4 yields 2 copper atoms, a nitrogen molecule, and 4 waters. And that's a plus. And that's it. Right? All of a sudden you feel like I'm earning my money. But guys, with that said, you will not see this on the test. So what will you see on the test? This. They would say, balance this half reaction. Guys, I've been doing this a long time, and I've never seen a question on free response where it says balance this. The only things that I've seen on the AP test have been balance this half reaction. I haven't seen balance the whole thing. Guys, if you see balance the whole thing, again, it's first time, never know. My advice to you would be skip it. It's probably only worth a point, maybe 2. You're probably going to get it wrong anyway because you're rushing through the test, and as you saw, any small mistake screws everything up. So guys, the only time I would say if they did give you balance the whole thing is if you needed that answer to do something later. I would say skip it and come back to it if you have more time. The other thing that you could see on the AP test, and it would be in multiple choice, is where I started with you and we put this on the board, this guy right here, and I really quickly ask you oxidation or reduction. You need to be able to identify this as reduction. Just boom, you got to know. So again, guys, they will have you balance half reactions. They will have you think through whether or not things are oxidation or reduction. It's kind of the extent of it. You guys good? Okay. So with that said, we need to practice with this, guys. And this is what that looks like. You've got this in front of you. And guys, we will review this after spring break. So then the question becomes, relative to this class, what's going on over spring break? The answer is this. You guys are now doing your last review hours, right?
Yep.
Okay. And so, guys, when we get back after spring break, we will review this homework assignment. It will count as a homework assignment. We will turn in chapter 20 summaries. And unless I'm missing something, I think that's it. Does that seem right to you?
Do we read in the summaries?
Right after spring break. Yeah. Yep. So, chapter 20 summaries, this assignment after spring break, you have no review hours, right? We will record the review hours you're doing now. And guys, really, let break be a break. You won't have any lab stuff either. So, it's just chapter 20 and this assignment. Are we good? Okay, I'm going to stop recording.